All right, so oxidation state, also known as oxidation number, is the number of electrons gained or lost in a state. A couple of simple rules to help figure out the oxidation state of something. Should be a review from last year. Pure element's going to be 0. Okay. Fluorine is the most electronegative element on the table. It's going to be -1. Okay, it's going to always win a tug of war for electrons, no matter who it's bonded to, including oxygen. Oxygen, being the second most electronegative, is going to win the tug of war for electrons every time it bonds with anything except fluorine. Okay, so it is going to almost always be -2. Okay. If it bonds with fluorine, it'll be +2. If it bonds with itself, another oxygen, it'll be -1. So it's not more electronegative than fluorine, and it's not more electronegative than itself. Okay. The only time this situation is going to occur in peroxides. All right. Alkali metals, what column is that? First, good. Alkali earth metals, second. Okay. Alkali metals is going to be +1. Alkali earth metals is going to be +2. Okay. All right. So after that, let's see. Trying to make this as broad and simple as possible. Ions equal their charge. That includes cations and anions in an ionic compound. Right, so if you had sodium chloride, for example, sodium's going to be +1, chloride's going to be -1. Okay. It's +1, -1. Cation anion bond. So its oxidation state is +1, -1. Okay. All right. Now, all of that leads to, in some chemical reactions, oxidation states get changed. Let's call it oxidation reduction reaction. It's kind of a mouthful if you try to say that too much. Oxidation reduction reaction. So that's been shortened to redox reaction. So a redox reaction is one where the oxidation numbers are changing. You always have to change two numbers. Somebody has to go up and somebody has to go down. You can't ever have two going up or two going down or one going up and nobody going down or whatever. That doesn't work. Somebody's going up and somebody's going down, because a redox reaction, we do want to write this down, is an exchange of electrons. Exchange of electrons. How do you spell it? R-E-D-O-X. Redox. R-E-D-O-X. Okay. All right, so somebody's oxidation number increases or is oxidized. Somebody's is decreased, or what we call reduced. Whoever gets oxidized is the reducing agent. This gets a little confusing. Whoever gets reduced is the oxidizing agent. So it takes two to tango, okay? Somebody's got to, this is an exchange of electrons. Somebody's got to give up electrons. Somebody's got to take electrons. If I'm giving up electrons, I'm being oxidized. and I'm doing the reducing because I'm giving you negative stuff, okay? If I take electrons away from something, I'm oxidizing that something, and I myself am being reduced, okay? So the reduced substance is the oxidizing agent, and the oxidized substance is the reducing agent. Electrons coming from one thing to the other. All right, that takes us to the question, I think. Zinc is used to reduce other compounds in chemical reactions. That means it's used to give electrons to other things. Zinc is a metal, correct? We should know from previous class that metals like to give up their valence electrons, correct? That makes them potential reducing agents, okay? Those electrons have to go to somebody else, gives them to whatever else. It's going to reduce that other thing, and zinc will be oxidized, okay? If a chemist needs a substance that is more effective in its reducing ability, which of the following species would be the best choice? So which of the following four things would be most likely to be a reducing agent? Physically, what do you have to do to be a reducing agent? You have to give up electrons. You've got to have them to give, and you got to want to give them up. Okay? So which of those four has electrons to give and wants to get rid of? Okay. Potassium has some electrons. That's potassium plus, right? Does it want to give up any more electrons? Looks like it's already given up one. So sodium, right? Okay. So sodium has electrons. It's got one that it doesn't want anymore, correct? It's got a valence electron that it would love to get rid of, just like zinc's got two of them it would like to get rid of. All right. The H plus doesn't have any electrons left at all, right? Potassium has some, but none that it wants to get rid of. Chloride, the negative ion there, it gained an electron to make itself stable. It certainly wouldn't want to give it back. Okay, so it would be a very poor reducing agent. So sodium would be the best of that choice. Sure. All right. Everybody follow that?
Yeah.
All right. Now again, like I said, these are kind of random, so we go to the next question. We're going to be on another topic. Okay. Hope that works for everybody.
I mean, my sandwich.
I'll let you know when you sound.
I just learned something weird.
0.35 gram sample of lithium is placed in an Erlenmeyer flask containing 100 mils of water at 25 Celsius. Let's get an Erlenmeyer flask out of the cabinet over here so you know what that looks like. You all seen one before, you just don't know what it's called. This is an Erlenmeyer flask. It's got that little triangular shape to it, okay? So that it helps prevent spillage. You can swirl it, shake it, and things might start bubbling and popping, and it's less likely to spill it because of the narrow top. But yet it's got a nice flat bottom. Do all kinds of stuff with that. All right, if it's got 100 mils of water at room temperature, okay, and lithium is placed in it, okay? All right, a balloon is placed over the mouth of the flask to collect the hydrogen gas that is generated. We've done a similar thing last year, right? We filled the balloon with hydrogen. That was magnesium and hydrochloric acid. Okay, I remember the balloon filling up and blowing it up. People videoed it, all kinds of stuff. Okay, so this works the same way. All right, different reactions, single displacement. This is a really hydride and a single displacement. But lithium is going to react with the water to produce hydrogen gas. Okay. After all the lithium has reacted with water, the solution in the flask is added to a clean, dry burette and used to titrate an aqueous solution of monoprotic acid. This is not going to be anything new with the question, just that. The pH curve for this titration is shown in the diagram below. So we'll come back to titration in a few days. All right. I don't think that has everything in this question. It might. Yeah, here we go. So what will be the effect on the amount of gas produced in the experiment if the experiment is repeated using 0.35 grams of potassium instead of 0.35 grams of lithium? Okay. First thing I want us to do is this. Take two minutes and write the balanced equation for lithium reacting with water. You need to pull up those step-by-step how to write a balanced equation. It's linked in the slideshow. Might be a good idea. What kind of reaction do we have? Yeah. Or what? Or an anhydride, right? Okay. It's not a synthesis.
So what would it be? Would it like it could either be a metal hydroxide? What's a metal like a metal hydroxide?
Well, what are we reacting with water? Metals. So metal and water, right? Is that one of the three types on the list?
So it's a metal hydroxide.
Yeah, so you're going to get a metal hydroxide and hydrogen gas, right? Okay. All right, so the metal hydroxide would be lithium hydroxide and hydrogen gas. Don't forget that hydrogen is one of the 7 atoms. Okay. All right, everybody good with the reactants and products? We still got to balance it, right? Okay. All right, the reason you can also think of this as a single displacement, okay, is what's really happening is the lithium is kicking one of the hydrogens off the water, right? So, this is the same idea. If you thought of water as an acid, which water, we'll learn later, can behave as both acid and base, let's do it. So if you think of it as an acid, then that metal is displacing hydrogen from an acid. It's not really an acid, but it's kind of. Or it's just an anhydride. However you think of it, it's the same thing. All right, so how would we balance it?
Well, hydrogen on that side has 3 and that has 2, so would you put 2 on this side, put 2 in front of the lithium? Would you give lithium 2, hydrogen 4, and then
Put the 2 right here,
well, you have to put a 2 in front of the.
which means you got to put a 2 right there, which means you got to put a 2 right there.
Yes.
Everybody follow that? Let me show you another way to think through it that'll give you the same answer. Sometimes a little quicker, sometimes not. Sometimes it's almost necessary to do this thing. All right, what I'm about to do prevents some of the back and forth, which you can sometimes get lost in. All right, so I got a lithium and a lithium, that's good, right? I got an oxygen and an oxygen, that's good. The problem here is the hydrogens, correct? There's 2 over here and 3 over there, okay? Now how many's over here? Still 2? How many's over here now? 2, right? 1 plus half of 2 is 1, 1 plus 1 is 2, right? Okay, so that's balanced, right? Okay, so if you're just balancing it to be balancing it, that's actually fine. If they're asking you for coefficients, they will most likely almost always say whole number coefficients. So how do I fix it to get whole number coefficients? I'm going to multiply everything by 2. Okay. 2 different ways to do it, end up in the same place. Yep.
So lithium was plus 2, why isn't there 2?
1/2 times 2 is 1.
Because the 2's can.
Isn't another easy way just to multiply the opposite? Like if you have,
2 and 3 to make it both. Yeah, if they're split up, when they're split up, that gives it easier. So the hydrogens are in two different substances on the right. That's not good. Okay, so this lithium is reacting with water to produce hydrogen gas in a 2-to-1 ratio, right? So we're going to get half as many moles of hydrogen as we have moles of lithium, correct? Let's get back to the question. What difference would it make if we use potassium instead of lithium? Okay. Well, potassium and lithium are in the same group, right? They're both alkali metals. That means they're going to, as far as balanced equations and electronic structures and all that, they're going to do the same thing, correct? All right. Potassium is a little more reactive. It's going to react a little more vigorously, a little faster. Okay. It's going to do the same thing. So same equation. Okay, same equation. So it's going to happen the same way. This was just going to happen a little faster, might be a little more dangerous. Okay, this might get away from you a little easier, might blow up on you or something. The balloon might fill up fast and pop on you. It's going to be a little more vigorous because that valence electron that this is losing, okay, we'll come back to that redox thing here in a second, is further from the nucleus, right? So it's going to get rid of it a lot easier and a lot faster. It's basically going to just happen really fast, okay? So, speaking of losing an electron, this is all redox, right? If we come up here and think about oxidation numbers, lithium's was 0, oxygen's is -2, these hydrogens are each +1, this lithium is +1, that's a -2, and a +1, and that's a 0. Those pure elements are 0. Ionic compounds have whatever they charge would be. Hydroxide is a covalent compound, so this is -2. This is +1 because hydroxide has the total -1. You remember doing that last year? It's a little process of elimination algebra thing. Same thing here, that this is -2 and the whole thing's neutral, but these each have to be +1. So the lithium is increasing 0 to +1. It's being oxidized, right? The hydrogen is going from +1 down to 0. It's being reduced. So it's a redox reaction. Okay. Same thing's going to happen down here. It's just going to happen faster.
Why is the lithium right here 0?
Because all pure elements are 0. That's its pure form. So
And
it's
you
a
said
0.
the H2O or the H is going to 0.
Yep. Pure hydrogen's a 0. Even though it's diatomic, that's still the pure form of hydrogen. So it's 0. Exact same thing happens here. It's just potassium instead of lithium. Okay. Now back to the question. What will be the effect on the amount of gas produced if the experiment is repeated using potassium instead of lithium? Same masses of each one. One's potassium, one's lithium. So the amount, okay, that's produced is going to have to deal with the amount that we start with. But in chemistry, we don't think of chemical reaction amounts in terms of grams, but what? Moles, okay? Moles. So 0.35 grams of lithium and 0.35 grams of potassium is not the same amount, okay? Moles. So the number of electrons are going to be transferred here, and therefore the amount of hydrogen that we produce is not going to be the same, okay? So find the moles of lithium would be dividing by 7, that's going to be 39. Okay? Which one of us is giving which one of those is giving the bigger number? Dividing by a smaller number gives you a bigger answer, right? Okay. So this is the larger answer here. This is the smaller answer. Okay. We're going to have to get actual numbers, all right? So the lithium reaction is going to produce more hydrogen, even though it's going to do it slower. But you're going to get more of it using the same mass. Okay. So what answer is that?
Wait.
It's B.
Yes. B. That's just some gas. All right, see how that works?
Mr. Perry,
Yep.
I have one question.
Say a little louder so we can hear it.
Okay, so basically, the reason why we did like the 0.35 over 7 to find a larger amount of H2O.
That's how you convert to moles, right?
Yeah, no, I'm talking like which one you converted to moles. Like where we found out which one was larger, is the reason why the larger and smaller was because lithium has 2, because lithium and hydrogen both have 2 in the equation.
No.
So
Because 0.35 divided by 7 is a bigger number than 0.35 divided by 39.
something about more H is produced, that's what you said. That's what I'm wondering.
Yeah, because there's more lithium atoms.
Okay.
Number next. What else could we chew up instead out of this one? Oh, not today. No, this is for the whole.
It is, okay.
Oh, no, this gets us all the way through Thursday or Wednesday.
Okay, good.
Yeah, we're not, there's no way.
It's on Wednesday.
Day before the test.
Is the test on next Thursday?
Test or quiz?
These are 2 weeks.
Oh, what?
2 weeks. I'm
Oh,
sorry.
oh,
Next
Whichever
time, we
Thursday
have
it
a
is.
Oh.
Is our
I
quiz,
skipped the Thursday.
is our quiz on Tuesday, the questions that's gonna be?
Wait.
No.
Yeah, how are you doing?
What's up with him? Yeah, on Tuesday.
Ask me that. Where are we at? So we got a balanced equation up there, right? What kind of chemical reaction is that?
That is a chemical.
That is a single displacement. That is a metal displacing hydrogen from an acid, correct? That's a very common process, okay? That's the reaction we used when we did magnesium and hydrochloric acid to make our little hydrogen bomb last year. We may do that again one day if we get time, okay? Iron will do the same thing. It's just not going to do it near as fast. It'll do it. When a student adds 30 mils of 1 molar HCl to 0.56 grams of powdered iron, if you have it in powdered form, it might get pretty big on you. A reaction occurs according to the equation above. When the reaction is complete at 273 in 1 atmosphere, which of the following is true? So 273 in 1 atmosphere, there's that stupid Avogadro's principle, right? So y'all going to be able to remember that because you know it's the one I think so dumb. Nobody's got their lab at 273 Kelvin, okay? So we're not going to go outside in February and do chemistry, okay? I don't know why. But anyway, so there it is. Plus that reaction is exothermic. It gets hot anyway, so there's no way. Anyway, it's what it is. All right, so we want to figure out the stoichiometry of this chemical reaction. So we did this last year also, right? Okay. So we need to do it just like we talked about in the last question. We measure things in grams, in milliliters, right? But we do not do chemistry in grams and milliliters. We have to always convert to what? Moles, right? So we have to always convert measurement to moles.
Talking about pre-cal.
Oh, good. You always have to convert measurements to moles. If it's a solid, it'll be grams. Liquid could be milliliters. An aqueous solution will be concentration and volume. And a gas would be pressure, volume, temperature that would have to go in the ideal gas law. Or they'll use this stupid little cheat thing for Avogadro's principle. One or the other. So before we answer the question, we have to convert the reactants to moles. So 30 mils of 1 molar HCl, how many moles is that?
Oh, I did.
We use the.
Nope, that's only for gases. We use the equation that we used on the last test.
Would it be 0.03?
How much?
0.03.
Yep, 0.03.
How'd you get 0.03?
Concentration times volume. Volume has to be in liters.
You divide by 35,000.
All right, how much iron do we have? We're going to do that in your head. Think about it just for a second.
Oh, shit.
0.56 divided by 56.
1.
0.56 divided by 56 is not 1.
0.01.
0.01, right?
That's what I meant.
All right, so these two things have been mixed in a 3-to-1 ratio, right? Do they react in a 3-to-1 ratio?
No.
Nope, they react in a 2-to-1 ratio. So somebody is going to run out first, right? Somebody's going to be left
Rice
over.
papers?
These are
This would be a lot of
So
the
if he's gonna go out
last year.
faster. So if he's gonna have this,
Yeah.
no, the ACL's benefits.
I remember after this unit, like, you know,
We all like rice tables, so they go ahead and make this
I
rice.
love rice tables.
Moved on after I got
You
a
hated
55 on that
this?
test.
I
and
love
started
rice
doing more
tables.
stoichiometry, and I was like, oh, it's
To be fair,
it's like it never goes away.
Nope, it never goes away. This is what chemists do. All right, so
Well, those are these are the 3-to-1 ratio. The reaction is just
So then wouldn't FE
which
be?
one's going to run out first?
Should be a limited one?
0.01.
Iron's going to go out first, right? Okay. All right, so iron goes out first. 2 ways to figure that out, okay? One is to multiply this by 2 and see that that's smaller than it's supposed to be, okay? So if you're going to react iron with hydrochloric acid, all right, how much hydrochloric acid do you need? Well, you need this times 2. 0.2, which means this is more than you need, which means that's less than you need, all right? That's one thought process. The other thought process is how much product would you make? Well, this would make 101 moles of hydrogen. This would make 1.5 moles of hydrogen. Multiplied by 1 and divided by 2. Get that number. So the one that makes the least is the limiting, right? It limits the production of product. So this is the limiting reactant. Okay, which means it's going to do what?
Go to 0.
Go to 0, right? Which means this one will have some left over. And we will produce 0.01 and 0.01.
Oh, because we
Why'd
started
you
at
do
0.
Mr. Cato, how'd you get the 1.02
Do what now?
The 0.02 on the C.
Times 2 divided by 1. Multiply by where you're going, divided by where you came from. That. So you're always going to consume twice as much HCl as you do iron because they're 1 to 2. 0.01 times 2.
Oh.
You shouldn't
okay.
need a calculator to do 1 times 2.
No, I'm just trying to figure out, I was using 0.03, so I was.
Ah.
Oh, no.
All right, so now what in the world is the answer choices? Let's see. That says HCl is in excess. Okay, that's true. And 0.1 moles of HCl remains unreacted. Yep, that sounds like both true statements there. So let's read the rest of them. HCl is in excess and 0.02 moles of HCl remains unreacted. That's false. Part C, 0.015 of iron chloride has been produced. Nope, that's false. 0.01. And D says 0.22 liters of hydrogen has been produced. Well, according to Avogadro's principle, we would have 1 mole of a gas under these conditions right here. 1 mole is 22.4. Okay, so if we have 0.01, then we should have 0.22. We have 2 right answers.
That's your right answer.
No, you can't have 2 right answers. That's interesting.
19? I was pepper.
Hang on, I'm trying to figure out why it's got 2 right. What's going on?
Teachers, please pardon the interruption. At this time, please release all varsity cheerleaders and junior high cheerleaders for the pep rally.
Oh, I never mind. Yes. A is not correct. That says 0.1, not 0.01. Oh, that's dirty. That's just dirty.
That's dirty. Not them getting.
0.1, not 0.01. So that's incorrect. 0.01.
Trying to catch you.
There's 0.22 liters of hydrogen.
Mr. Good, I
See, if you
Yes.
missed that, you don't get
Okay,
it.
so I'm confused on where you got, for the rice table, minus 0.02.
This is 2 to 1, right?
Yeah.
So these numbers have to be 2 to 1.
You should have told me
So for
that.
every mole that
Okay, I got it now.
did,
Yeah.
You did not say 2 to 1. You
So
said
you
1.1.
third time I've said
So
it.
you get 0.01 times.
Let me write that. You said 1.1.
So the change that takes place, that's the chemical reaction part, right? The chemicals react in the same ratio as the balanced equation, right?
Okay, thank you.
So the answer is D.
D, yes.
And
One,
we would
A
have-
is not right because the decimal's not in the right
And we would
place.
only give that
Ready,
final
sit
answer.
It's by knowing that.
Yeah, so you gotta know Avogadro's principle to figure that out. Like I said, they're very fond of it. I think it's stupid, but they're very fond of using it in their questions. So, there you go.
Thank you.
So if a mole is 22.4 liters, then a tenth of a mole would be 2.24, right? And a hundredth of a mole would be 0.224.
Yeah.
So, D.
Yes, I do.
How much, do we know what time we're getting out of here?
19.
19? It's just for the fun of it, look at the next question. It might be a quick one, who knows?
Oh, no, it's a lot of squares.
But that's the.
If it gets questions like this, then we have no.
Nope, I'm not writing that. No.
I know, I can't say the actual.
I will go back and.
I mean, you can say this.
Oh, I got it,
Yeah.
yep. I got it.
Just a cornball.
Yeah.
Just a cornball.
Every, what's the
Adult knows that.
Sure.
Alright.
Yeah.
We're not gonna have time for this one, but there's 5 identical 2-liter vessels filled with nitrogen and sealed. 4 of the 5 vessels also contain a 0.05 mole sample of sodium bicarbonate, sodium bromide, apparently nothing, copper, and iodine. As shown, the volume taken up by the solids is negligible. Initial pressure of nitrogen is 720. All 4 vessels are heated 127 and allowed to reach a constant pressure.
That sounds like a whole bunch of gibberish.
At that point, let's just.
Mass would be the same. Okay, so it's asking what's the difference in mass after you heat it up, the mass would be the same.
Why?
Why?
Yeah.
How do you,
Okay.
heating something up,
It doesn't change.
you weigh more in the summer than you do the winter?
Oh, yes, actually, I was listening. I was listening.
Gotta put on what it called. Is that the physical and chemical?
I be hibernating in the winter. What you mean?
That really
Hibernate under a tree.
A worm does.
Worms don't hibernate.
Only nuclear reactions change mass.
They like, no, they don't.
Dylan, you gotta.
Are you keeping that worms? They don't hibernate. If you see me in your. Yeah, why was
Hello, big girl.
Hibernate? Under a tree. In a cave or a No, mate.
I don't know. It's the open.
I do not do party.